Questions before I start? Today's just finishing up this SuperLearner lecture. And last time we talked about the fact that if you use the same data to fit the model and then evaluate the model, that evaluation will typically be biased in an optimistic way. Everyone has this intuition about that. And this just helps us to go to the next step, which is how do we evaluate these in a way that's unbiased so we can choose among competing models what is the best model. And I essentially went over this yesterday. I mean, the inference, it could be the estimation's okay when you do this, not always the case, but the inference, particularly when you're talking about prediction equation, prediction functions that you're coming up with, estimated predicting regressions, for instance, that their assessment is certainly biased, and therefore the inference that you might derive for other parameters is going to be biased. That's based on that model because you're essentially underestimating the error of that model to predict. And the obvious case to think about, which where if I had 3 points and I fit a quadratic model, it's going to go through any 3 points, right? That obviously, no matter what I do, it's always going to look like a perfect empirical fit because there's going to be zero residuals. So if the number of basis functions is the same as the number of levels, then you're going to get a saturated model. It's going to go right through the data. And if you have no ties, so you're fitting something that has the same number of parameters as a sample size, then you, of course, get absurd fit, but it's going to look great empirically, right? So you can take the extreme example and no, it doesn't work in general to do this and come up with a prediction model where you can really trust the measures of fit, like an R-squared fit to a linear regression where you do a lot of adaptive stuff. If you don't do a lot of adaptive things, it's this preset model, then in that case, it's there's a little bias, but it kind of goes away. Sample size gets large, it's not that important. And that's true even for things that are a little more adaptive, like smooths. It's really not terrible. But we're going to talk about things that are really adaptive later that really try to find any kind of bend in the function that will do a better job predicting that's real. And in that case, if you don't do it carefully, you can get severe overfitting. And it really means that any approach is going to be consistent in terms of deriving both an estimator that's working relatively well and getting an idea about how well it fits. It's going to fit for future predictions, for instance, means it can't be ad hoc. It has to be supervised. It has to be basically an algorithm-driven kind of procedure. And therefore, it's really important that you get the algorithm right. I can come up with, there's tons of algorithms out there for prediction. And some of them will do great in some circumstances, and some of them, and those same ones will do poorly in other circumstances. If we're going to be choosing among them or choosing among many linear models or logistic models, whatever it is, in order to get something that we can really trust, one of the components of that is it's going to have to be an automated algorithm, which are called machine learners, and that they explore the space in some preset way. It's not you trying interaction terms and then putting them in, taking them out, and doing that sort of thing. That's where you can derive fairly serious bias. And really right now I'm just talking about prediction and the error, but that bias will translate into the estimates of causal effects, for instance. So, you have to specify the candidate ahead of time. And again, those candidates themselves will do something. They'll have model selection procedures built in, but it'll be algorithmic. You won't be, sitting there tweaking things and looking back and forth with the data a lot. It's going to be basically like a machine. You press a button, it's going to go through a set of candidates, and that's really leads to this. So you need a pre-specified way to choose between these candidates, and that's what we're going to get to in this lecture. How do you do that in an optimal way? We're going to do something that's both intuitive but also has theoretical justification. And so basically you want the inference in some implicit way at least to include all the selection process too, right? That it adds a source of variability, and you want to make sure that you're capturing that variability correctly. That's probably one underlying reason for a large number of false positive studies that apparently the literature is littered with, is this kind of pre-specification is not common in many fields. It's getting more common, and there's a whole open science project here on campus, and it's really that the idea of pre-specification is spreading across many fields, particularly in the social sciences, and it's going to start affecting epidemiology and public health kind of studies, I'm sure of it, not too distant future. We're not as bad as others that have more unconstrained ways of fitting the data, but we're not great, historically, particularly since the advent of the personal computer. It's very easy to do ad hoc model selection, and we've done a lot in our field, and probably not to the benefit of trustworthy findings. So again, we refer generally here to data adaptive estimation, meaning the model that we may end up with, we may not know ahead of time, right? So we're going to adapt what the machine is going to adapt to what it selects based on the data. So the idea is to get away from pre-specifying a particular logistic regression model or a particular linear regression model. The idea is when you don't really know that those are the true models, you want some way to explore what you think is the space of true models. And if you don't know much about what the true model is, that space is large. So the little you know, the number of possible models is bigger, right? And the more you know, it's smaller. And that's it's always good to include information, real information, the estimation of these models. But I have to say, practically, often that comes down to us. It's like we know that, as I mentioned before, that we mean that the y is bounded in some way. And there's ways to make sure that our predictions are also bounded. And that can help quite a bit, and particularly in non-huge samples, where just the variability of estimation can lead you to predictions, let's say, outside 0 and 1, if I'm using a linear model to predict, for instance, something that's binary. And therefore, I know can't be greater than 1 or less than 0. Just to note that machine learning and automated algorithm from learning from data, that's what machine learning is, right? And it's a big topic right now. A lot of press talking about machine learning. There was big news this morning. Did you guys read that in the New York Times about the top Go player in the world being defeated by what is essentially a machine learning approach? I don't know that much about this particular Google project, but what I hear is that it isn't really based that much on first principles about Go. It's very empirically derived. They play a lot of games, and the computer learns, like, okay, if I make this move, I don't do as well. If I do that move, and then it starts playing with itself and seeing when it loses, and it trains over time, and it's built this machine learning algorithm, which is I understand, and I haven't looked at the algorithm, so I can't really tell, that it's really trying to do it in an unsupervised kind of way, meaning it's not really using that much the rules of Go. I'm sure it's going to use the constraints in the prediction. It's a very large categorical prediction, right, over many moves ahead, and apparently the combinatorics are such that if you use first principles to do it and just sort of looked at all possible moves, it's impossible. There's trillions of moves in Go because it's so huge. So where you might be able to get away at some level doing that in chess, you can't in Go. And it's, I'm actually shocked that its machine is winning. It sort of changed my idea about the power of machine learning, because I figured in circumstances where we know the system, and our systems are always more complicated than Go, that you could gain a lot over a machine learning approach by knowing, something about the actual functions that generate the data in this case. But actually, it's turning out not to be so true. Yeah.
It's only 1 out of 5 so far, and they're going to play all 5.
Oh, it's only 1 out of 5. Okay, I haven't read the title,
Yeah.
and it's been circulating around for the last month, so I've talked a lot. There's been other articles about it, but yeah.
Yeah.
Okay.
1 out of 5.
Okay, we'll see.
He quit instead of losing.
Oh, is that right?
So that the machine wouldn't learn any more from him.
Oh. Wow, that sounds kind of evil. I know. I feel like maybe we shouldn't learn this.
Well, I'm saying I think that he was just he wanted to test it out.
Yeah.
And then now maybe he's changing his strategy.
Oh, that's
for
interesting.
games.
Okay, well,
I think
I
we
may
should
have a
look
different
for
story.
humans.
I mean, I was shocked, so maybe I'm shocked too early. Maybe in the end he'll figure it out. But anyway, in some ways, it's incredibly exciting because it means these are great tools to learn in the kind of systems we look at. But one also has to realize our systems are very complicated, many interacting pieces, and we don't know the rules. And so it's a bigger challenge. Okay, we're going to focus basically on two main concepts. One is called loss-based learning and V-fold cross-validation. Loss-based learning as a way to decide what we consider how we evaluate how well a regression does, and that's going to be defined by the loss function. That's not an objective thing. You can't say, oh, that loss function is better than that loss function. Typically, it's just something you choose because you believe that's the best measure of a failure, essentially. And there's other motivations which we'll get to. And then V-fold cross-validation is going to be a way that we rigorously choose between competing models, or in this case, come up with combinations of them that do an optimal job predicting in the future, according that optimality being defined by that loss function that you decided. So if you squared error loss versus other losses might derive different regressions, but they have different goals. So you can't necessarily say, oh, this one's better than that one, because you define what a mistake is differently in both of them. Here, just in the HIV example, just looking at, this is sort of like the simplest kind of machine, which is stepwise regression. That's a machine. You don't know what you're going to end up when you do stepwise regression. You don't know what terms are going to end up in the model. And in the simplest case, forward selection, you press a button, it searches for the best single predictor among all using typically the p-value, or it can use other criteria, but let's just say p-value for now. Picks the smallest p-value, puts it in, looks for the next term they can add, and then there's some stopping rule, right? That's the way these algorithms work. They're ad hoc by nature because there is no universally good algorithm for prediction. So just clever ways of exploring some space of models, and stepwise regression is a very effective way possibly to do that, particularly if you include things more than just the linear terms. Then you're really starting to explore a big space. I mean, in the limit, any relatively smooth function can be fit by some polynomial, right, which is some linear model in where the terms necessarily aren't linear. They might be squared or cubed, et cetera, right? So, in the limit, if you had enough basis functions, this should cover almost everything, even just stepwise regression alone. But of course, if you have discontinuities, it doesn't work as well. And there's other learners that allow things, for instance, a function that can just jump, right? You want things that will consider both smooth responses, dose responses, or smooth regression functions, and those that allow discontinuous ones, because you might have both. You might have this and then that, right? So the candidates, not any one candidate is going to solve every one of these, even though people advocate a lot for something called deep learning. That's supposed to be the new magical machine learning, and it does extremely well. I think it's underlying, some kind of deep learner is underlying this Go algorithm that they're doing. But particularly for our kinds of data, where it's not necessarily huge all the time, it's not necessarily millions, and in this case it could be billions of games it's playing. These kinds of very adaptive learners that really, are very aggressive in dividing up the covariate space and looking for different functional forms in each little section, kind of like this in this 2D case, can be really miserable performing. They can do terribly. So it's not a panacea for us. It's for people that are working in really large data, like internet transactions and things like that. Yeah, maybe it can cover a lot of that terrain, because even if it's highly over-parameterized, because it has to do a bunch of, I can fit like a line with a bunch of little step functions, right? But if my sample size is really, really huge, that's not going to be that bad, right? If I can really I can have like hundreds of parameters, thousands of parameters that define every little step that I make up there. And if my sample size is 1 billion, that's not going to hurt me variance-wise. You know, as your sample size get ginormous, then the fact that it's hard to overfit is basically the bottom line, right? Because that means you'd have to fit billions of parameters, and even millions of parameters might be such that it doesn't really affect the prediction error all that much relative to a much smaller model. And that's why I think in that field, they don't really worry about the kind of things we worry about, which is we really have to do good for all sample sizes and all kinds of functional forms, because we can't anticipate very simple systems, things like Facebook and Amazon, where you're looking at you know, a relatively constrained system trying to predict things like what ads will click on, et cetera, like that. And you have past, which is really the outcomes itself at different times. So it's very natural that you would use these kinds of procedures for that, because they end up being almost like nearest neighbor, where you just kind of find a person just like you that made the same purchases previously, and you look what those people purchased the next time, right? So these kinds of very adaptive things can do very well. I will just say one of my soapboxes is the computer scientists right now and are moving in to medicine and health. Right? It's a big push to do this, and they have a lot of interesting tools to offer, but they're coming from a really different perspective, because they're coming from either situations where you have infinite number of experiments because they're engineers and they can like tweak knobs and measure things and build a model that way, or they're coming where there's huge numbers of data points. And so the idea of optimally fitting in some way isn't necessarily as important to them. And they're coming and using these tools in situations where there's great optimism among them. I'm less optimistic that they'll translate. What I'm trying to give you today is something that will translate, that still could do well in that context, but assuming it's programmed to be able to handle large sample sizes, but also do well for very, very small sample sizes. And that's what we need in public health right now. We're not dealing very few are probably dealing with sample sizes, data sets that are terabytes in size, huge data sets. You're probably dealing with at the most, 50 gigabytes, which is not that big, and you can often handle with a personal computer, and probably are not that big, so you don't have to worry about overfitting. Anyway, this is just showing as example for a sequence of models, right? I can just get in with the same exact terms, right? I can make more and more complicated models. I'm not adding any variables here. It's just using them in more complicated ways, right? And as I said, since any sequence, since you can model almost anything with a sequence of polynomials and cross product terms, then this is not necessarily a bad way to do it, and we will do these kinds of approaches. But anyway, you get the idea. When people fit main effects regression here, that's just one of many models you would fit, and this is often the default without much consideration of whether we should consider ones with all, with interactions, all possible two-way, and then you can consider four-way interactions and three-way, et cetera. Like, where do I stop, right? What's the best candidate? And you can also see, in this case, if this is a true model, that has a very easy interpretation, right? What's the interpretation of beta 4? First, just the statistical interpretation. 241, this didn't just etch in your brain from the repetition. It's the log odds ratio for a unit change in A, keeping the W's fixed, right? That's what it means. That's a statistical definition of the odds ratio for any unit change in A. A is binary, which is the case that we're talking about. It's just the log odds ratio comparing, for instance, treated to untreated, keeping the W's fixed. If this is also the, if this is the true model and the W's block backdoor pass, so these are all the confounders, then this would be an estimate of the conditional causal odds ratio, using the same identifiability we discussed in earlier chapters. Anyway, beyond this, there's a lot more candidates. I can add, cubic terms, whatever, sine terms, et cetera. There's huge space that you want to cover, And doing this by hand is, you can see, impossible, right? Because it's even infinite in this simple example. So when you're choosing candidates, it could be, even if you knew the true model, you didn't know the actual coefficients, but you knew the true underlying form of the model, it doesn't necessarily mean you want to use that form for your finite sample size. For instance, I could have a very complicated model, is the true model, explaining the relationship to the outcome to A and W, but I have 100 data points, right, or 50 data points. And if the true model was that last one on the previous page, I'm not going to be able to fit that very well. The variability is going to be so huge from fitting such a complicated model with such little data that the variance is going to explode. The variability around, I'm not going to estimate any of those coefficients well. And so even in that case where I know the truth, I might do a better job in terms of prediction in the future using actually a model that's not the true model, which means it's a biased model, right? And it may have much lower variance, even though it's obviously adding some bias because it's not the true model. And of course, that's what we're not going for the true model. You have to remember that. We're going for the optimal model with regard to a loss function given the data set we have and the sample, which is the implied sample size we have. So we're really trading off these two sources of error, the bias, meaning it's not the true model, and the variance, given the variability, let's say, around of the predicted model in repeated experiments of the type you did to derive that estimator. And so, generally things that are small models, few coefficients, let's say in a linear logistic model, will have low variance and higher bias because they're not as flexible. They're not able to bend to the function as much. Those with lots of parameters, lots of basis functions, are able to bend around a lot more to match different kinds of functional forms. They'll have lower bias and higher variance. And we want something that trades those off optimally. Overfitting, I've already discussed. So overfitting is basically fitting a model that's too complicated for the data in hand. You can get that way. And overfitting also is related to the evaluation of the fit of the model. So an overfit estimate of the mean squared error is one that's not accurate because you're using the data for both and you're getting an overly optimistic estimate of how well it will do in the future on a new data set. And that's just comes here. This is how big a problem this is now. I think it's probably getting less over time as people realize that this kind of approach leads to all kinds of erroneous results, but it still happens. As I said last time, I rarely have, if I come in with a model that we agreed to back in the days when I was doing much more standard kind of regressions, and it turned out that the exposure of interest was not significant. The first question I get is, well, did you fit an interaction? And I'm like, well, would you have said that if I told you it was significant? And you can see right there that's a bias, right? Because the inference isn't going to account for the fact that my even selecting that next model is conditional on not rejecting the null of the first one. And that's going to lead you down the primrose path to something that probably is not reproducible. And that standard error, just to remind you that you get at the end for these parametric approaches, always assumes that you've pre-specified the model. Now, there are circumstances, if the sample size is really, really huge, and you're not using an approach that's super adaptive, like stepwise regression is not that adaptive. It can't bend that much, let's say, to the data. It's probably not a terrible measure of the fit, even if you use the data for both. But if we don't know that's the case a priori. That's also a function of sample size. So where that may be true for a sample size of 1,000, it could also be not true for a sample size of 100. There's no universal thing I can tell you that says, okay, you don't have to worry about it now. I'll have a gut feel. If you tell me you have 1 million sample size and you did main terms stepwise regression, I'm not going to be worried about your R squared. It's probably fine. It's probably not overfit because the class of models is not enormous. It can't really adapt that much to the data. and the sample size is large enough that in repeated experiments, you're probably gonna end up with the same model every time. So that's variability, even though you're not pre-specifying that model, it essentially is pre-specified, because any repeated experiment where you get a new million and do the forward selection, you get essentially the same model every time. And you're not, that variability from the model selection goes away. And that's possible. And therefore, for giant sample sizes, maybe one doesn't have to worry about this. They're using a set of procedures that aren't super flexible. But again, we don't want to work that way. We just want something we press a button and it just works regardless of the sample size. That's the goal.
Alan,
Yeah.
how would you do with the case if you have an independent training and test set?
Yep.
And you go through and you try a bunch of different prediction algorithms like SVM or
Yep.
logistic or whatever, and some do really well.
Yep.
When
On the testing?
measured on the test set, yeah, and some do very poorly. I mean, it's also bad to just cherry pick whatever algorithm.
Yeah, but
you
there's a
want.
theory that tells you how much you can try.
Okay.
And then that underlies the algorithm we're going to talk about. It's a great question. Because you can imagine if I tried, 100 models,
Yeah.
maybe it's okay. That's not a huge number, it turns out,
Okay.
given
Oh,
the theory.
really?
Well, it depends on your sample size, but if I tried 1 billion models, I know one of them randomly is going to do well, right?
Right.
And so at some point you're going to overfit even with the test set. Well, it turns out that the number of things you can try has to be a polynomial in sample size. So that's essentially, as long as it's less than n squared, you're okay. That's what the theory says. So basically for you guys, that means you can't try enough. You simply can't do enough to where you can get that accident happening for
Okay,
most
so if
practical
you tried-
sample sizes.
If you tried like 5, and
You're
you
fine.
found a really good one, you
Yeah.
could just report that good.
That's what we're going to do,
Okay.
essentially. Yep. There's a lot of solutions to this problem, and including using types of fit statistics, which try to penalize you for the complexity of a model. AUC is one, and there's BIC, MALO-CP. These are really attempts to take the empirical fit you get by using the data for both and penalizing that fit for the complexity of the model. And there's like very particular circumstances for which you can justify AUC theoretically. Really, where the biggest possible model is some linear model, so that's really small for us, but let's say that's the case, and you're looking at different submodels of that, and you're doing maximum likelihood estimation, and that's of course appropriate here because you know what the true model is, the space of the true model at least covers a very small, relatively small model. In that case, you can theoretically justify AUC, but it's really almost the only case. So these are really ad hoc techniques for the most part. There's a lot of theoretical work that goes on in them that tries to make them more generalizable, but and it's not like they miserably fail all the time, but they don't have strong theoretical justification for what we're going to do. Yeah.
Do you mean AIC?
Oh, I'm sorry. AUC is a different thing. Yeah. Thank you. AUC is area of the curve. AIC, Akaki's information criteria. Thank you. And there's variations within these two. You can penalize by the number of parameters in different ways, and there's a lot of sort of ad hoc tweaking that may do okay in individual circumstances. Again, it's not where I can have a universal machine now that works all the time because it has to be justified for the particular data application. So it's not optimal. And again, there's no guarantee it's going to work in what we're doing. And so we're going to focus on what's this called loss-based estimation. Okay, we have to define what loss is, and it's really going to be a function of what we think best would be. So right, they're inverse related. What loss means, that is a mistake. Best is something that makes the least mistakes, right, or the smallest number of errors, or the errors are smaller. And we're going to talk again. We're really talking the context of this prediction function that we need for that substitution estimator. So we're going to be talking about estimating this regression. Again, this is the mean of y given a and w, and this indicates it's the true model is Q0, and And so we're going to make estimates of that function. You can think of Q bar 0, A, W is a big function in A and W. I put in an A, I put in a bunch of W's, it gives me a number back, right? That's what a function does. And so we're obviously like to get close to the truth because that'll give us an unbiased estimate of the causal effect if we use it. We want to know how do we get as close to the truth given our sample size, et cetera, and given what we know. So first of all, we have to define best very explicitly. You can't just say, oh, I want the best model. You have to say best with regard to this criteria, and that criteria is going to be a loss function. A loss function takes in an observation, and it takes in some prediction function, and it returns a number. It's an element. It maps that into a real number. It just tells you, for instance, squared residual is a number that if you put in the true value of the observation, it's y, a, and w, and you put in what the prediction would be for that given my current model, then it'll map that into, the predicted minus the truth squared, for instance, right? And that loss would be squared loss, as we'll see. And that's what I have right here. So this is one example, squared loss. Every time I put in the observation and I put in the prediction, it returns this number, which is just the residual squared error loss. That's one. Another one is for let's say y is binary. And so the likelihood is just a function of the probability itself. QA, in this case, QAW is going to be the probability right? And therefore, the likelihood of a binomial observation, y, is simply the log likelihood in this case, would just be taking the negative out, is that times this, right? If y is 1, then that's the probability. Oh, cancel. If y is 1, then this is the probability. It's raised to the 1, right? So you just get that. And if y is 0, well, it's 1 minus that, right? And you get 1 minus this, raised to this power. So this term only comes up when y is 0, and this term only comes up when y is 1. And it's the probability of observing that y. And then you take the log of it. That's the log likelihood for a binomial. But of course, the higher the likelihood, or the log likelihood, the better the fit. So we take the negative of it. So that means that now the bigger it is, the worse it is, right? And that's what we want. The loss functions have to be the bigger it is, the worse the error is. So it's another example, right? And it turns out, there's many examples we're not going to go over, like misclassification, etc. Now, how do you choose the loss function? Well, one way to choose it is just because that's the error you care about, right? I care about squared error loss. For some reason, how I'm going to use this, that's the most important kind of error. You could imagine another one being misclassification. If I have a binary outcome, that if I make a mistake and say someone is diseased versus not diseased or vice versa, that's the worst kind of error. That's the error I care about. I want to reduce misclassification error. That's a different kind of loss function. And there's other ones as well that you could derive. But one way to justify it is you want the procedure that's trying to minimize the loss function, and if you knew the truth over all possible values of the regression, if you minimize the loss in the true population, so you can think of this E0, L0, Q, so Q bar is fixed now. I've done something, I've got a prediction function. That's Q bar, okay? You with me? Whatever I did, it's fixed now. Then I have the entire target population now. I have everybody I care about in the target population. So for every person, I could get their loss now. I have their observed outcome. I have what I predicted for them. I could derive the loss, whatever I define it to be. And then I could get that, particularly the average of all those loss functions in that. It's called the risk right there. This is called the risk, just the average of the loss in the target population. Average loss right? And if I say, okay, I'm going to try all possible functions and minimize that, I want to choose the loss function such when I do that, I get back the truth. I get about the parameter I'm trying to estimate. So it turns out some types of loss functions, when you choose them, and you know, at least if I had everybody in the population, I want it to do the best job, right? I want it to converge to the thing I care about, which is trying to get, for our causal inference estimate, we want to get Q right. And therefore, that's one way to choose it. If I choose other kinds of losses, like I choose absolute loss, it's not going to return the mean of y given a and w. Will return something else if I minimize it, all those things. It returns a different parameter. So you basically choose the loss function to give back the thing I'm trying to model. That's one motivation, right? So that's obviously a good way to choose the loss function. It turns out that's not always unique. Sometimes two different loss functions, when you do this exercise, and you can, in theory, put all possible Q bars in there and select the one that minimizes the loss, that two different loss functions will get back the same function. So it's not always unique that way. Sometimes it's chosen for other reasons, but that's the goal. Now, you can see how this would lead to an algorithm, right? Because now, if I replace this with, well, I have a sample, or I have a test, let's say I have a test sample now, and I don't have every possible function, but I have a lot of functions, and I'm going to try to minimize the average loss, so how I want among all those to find the one that gives me the closest. That's the exact equation here, where I'm just plugging in these with Pn, right? This is just the E with respect to the observed data in that test sample. And then this is just going to be over a bunch of candidates that I have. I don't have every candidate. And hopefully then it will generate back something that will be closer to the truth, right? It's a procedure, it motivates a way of choosing, which is, okay, well, I should now choose it based on the fact that I don't have the target population but a sample. However, you want to make that sample, make sure that sample has certain characteristics, like it wasn't used to fit the Qs in the first place. And we'll see how to do that in a sec. So, for instance, if we're trying to model this, which we needed, just to remind you, right, we needed this for the average treatment effect, right? Because, just to put it back up here, it was E0, W, E0, Y, given A is 1 and W. Our parameter is a function. I can write this as Q bar 0, 1W, and this one as Q bar 0, 0W. That it's a function of those conditional means, right? So I like my loss function when I minimize it in the true population over all possible models to yield that parameter, because my estimator, when I plug in these things, estimates for Q0, will rely on getting a good estimate of that Q0. And therefore, I want to choose a loss function where I'm doing the appropriate minimization. It's going to give me the right thing. Well, it turns out if Q0 is this conditional mean, that doing this procedure will yield the Q0 I want. So minimize if the loss is this. So squared error loss works. If I just define my squared error loss, my loss is squared error, just the observed minus the predicted squared, and I do that exercise where I try every possible Q and minimize over all possible Qs in the target population. When I get that average risk, it's going to yield me, the one that minimizes is going to be the true one, right? So that justifies using squared error loss when my thing of interest is the regression of y on A and W getting the conditional mean. But it's also true for this, right? It's also true for negative log loss in this case. It's true for both. And the one big difference is this only works if Q is not only an estimate of the mean, it's estimate of the probability, and that works when, y is binary, right? And so for binary y, this is an obvious choice, but this choice also works for binary y. They both work. The problem is, usually when you're using this as a loss function, you're doing regressions, let's say linear regression, and it doesn't guarantee the prediction is going to be between 0 and 1. If you're using the appropriate functional form for Q here, so it actually is generating a probability estimate, a value between 0 and 1, then this will guarantee that Q also, 0 falls in that, between those bounds. So there's obviously a gain that can come from using this one, the lower one, over this one if your outcome is binary, because this one won't guarantee necessarily that your regression function is bounded. Much of the reason why you do logistic regression when you have binary outcomes, because it guarantees that that estimated mean or probability is between 0 and 1. Okay, so now we have loss functions. And we want to minimize that loss function. That's also the same as minimizing the mean squared error. It turns out the risk is the mean squared error here. The E0, y minus q bar AW squared is defined. That is the same as the mean squared error, right, of q bar. So the risk is mean squared error. Mean squared error, of course, has intuition, but beyond this justification. And so L2 loss, this is also called, let me go with it. And again, the intuition now, when I do this in practice, I'm going to put in different Qs now that I fit. And I want to find the one that minimizes the mean squared error. We're going to talk about how to do that. That makes now that variance bias trade-off more obvious, this particular loss function, because I know mean squared error is equal to the bias squares plus the variance, which we went over earlier. So you can see doing this is going to try to balance these two. If I'm really trying to minimize something that's a good approximation to the true mean squared error, then I should be also trying to get this balance right. It's more explicit, meaning it's automatically balancing the complexity to give this balance between bias and variance the right balance. As sample size gets bigger and bigger, this term goes away, and it's this term you concentrate on. When it's small, it's vice versa. So biases becomes very important for very big sample sizes. That's the thing you want to target, because you don't have to worry about variance. And variance is the thing you have to worry about more for small sample sizes, because that's the bigger problem. And reducing bias is hopeless in that case, because to do so down to 0, we'll have a model. It's just too big, probably, to be any good. So the key is I have to estimate, in this case, the mean squared error accurately. And again, I told you, and you understand intuitively, I can't do that by fitting a very adaptive procedure on the same data by which I derive that prediction, right? To get the empirical mean squared error, what do you do? Let's say you're going to do stepwise regression. So you do a procedure, at the end it converges to some prediction function, and at that point, how would you derive the empirical mean squared error? Just using the same data used to estimate the regression. Yeah, you first would predict for every observation based on their A and W what the Y should be, right? You get the Y hat, the prediction from that Q that you end up with, that Q bar you end up with. So that's the first thing. Then you, of course, make your loss function, which in this case is just the square root of 0. So you take the predicted Y minus the observed Y and square it, and then you take the empirical average. You get back what you get back from the standard regression procedure, right? That's what that mean squared error is, right? And I'm telling you that doesn't work, but what would work? What we think, one thing we know would work if I just had a completely different data set from the same data generating distribution, and no matter what the size is, right? I've used 1,000 to estimate my regression, but let's say I happen to have a test data set to evaluate it that's 10,000, right? I could just, in that case, since wasn't used at all, it's completely independent, I can estimate unbiasedly, just doing the same thing, just predicting in that new data set, and then getting the residual, squaring it, taking the average. Right? There's no dependence between that residual and there's no dependence between the residual and the fit. All that goes away because it's completely independent. That fit was made in independent data, has nothing to do with that data. So I don't have to worry about that overfitting there. In that case, that'd be great. Then I can compare models there, just as you pointed out earlier, and use that to choose. And that's an unbiased estimate of the mean squared error. So that should do a good job. If I choose the one with the lowest mean squared error, that should also be choosing, at least in the limit, the regression that does the best, right, of those candidates. And that's, we just have to trick the data we have to do that. That's all we're doing. Really, that is the only way, is just to have an independent data set. That's the only way that always works, no matter what the context is. I don't have to invoke special context for BIC or AIC. That will always work. So is there a way to have data in hand, do both, independently test your fit and fit it? And the answer is yes. You just have to divide up your data into bits, and that's what we'll get you next. And I'll stop here for 10 minutes. So cross-validation, that's how we do it. Use the same data to both fit. When I say candidates, I just different algorithms we could use to fit the data, including standard ones like simple regression. Even just taking the mean of the outcome can be a predictor. And so how we fit it and also evaluate it in the same data is we split the data in different parts, and we fit it on some of those parts and then test it how well it fits on the other parts. That's called cross-validation. There's many ways to do it. And we're going to concentrate on V-fold. V is just how many splits you make. And we'll talk a little bit about how one determines that. But for learning it, the easiest way to think about it is I'm going to split in two. And then go in more detail in a sec about how exactly we arrange that. But there's lots of types of cross-validation. The general theory that is used to develop our algorithm applies to any form except for one, which is leave one out cross-validation. That actually might work in some circumstances, but not really theory there to justify it, and we know it won't work in others. So leave one out is the one that we can't rely on, and you can imagine you don't get a great estimate of risk in each leave one out because it's a sample size of one, and that gives some intuition why the asymptotics that require the estimated risk in the validation set is done well, breaks down if in fact I'm never going to make it bigger than one. It has to grow at some level. So anyway, that's for those who care about the theory. That's why leave one out is hard to prove things. I think the intuition is we have intuition that it probably does work, but it's a hard thing to prove. So B-fold is what we'll count. And also I should say there's random sorts of cross-validation. You randomly draw data, and then and you keep on doing this over and over again. And this fits within that framework as well. So it's like these forms of cross-validation aren't necessarily the wrong forms, but it doesn't turn out in the end, it turns out not to matter that much. And two, things are implemented for V-fold cross-validation, and the theory is easy to prove for it as well. So basically, this is how it works. In this case, we'll have V is equal to 10, right? So we're going to split the data in 10 parts. And for the most part, for a typical study where you just have a random sample, then you'll split just randomly, right? So they're equal random splits of the random chunks of the data. This can be generalized where, for instance, I might have repeated measures. So the same individual is in my data set more than once, and therefore there's some expected dependence between observations on the same individual. You can structure the cross-validation to make sure now you keep the splits independent because you actually assign people to the different V folds, and not just different observations. So you keep everyone's observations together in the same fold and avoid this problem. You really have, however you do it, it has to be where the validation sample is really going to be independent of the training sample. So anything that causes a dependence, you have to structure your cross-validation to get rid of. And that usually be fairly intuitive. Most procedures that use it, that we're going to talk about, allow you to structure the validation, the cross-validation that can keep track of observations that are correlated in the same, keep them in the same validation sets. And so you split them up. Each will have sample size N over V, of course. You're just breaking up the sample size by V in this case. This is for tenfold right here. And for the first step, there'll be, well, here are some terms. There's the learning set, which is just everything. The training set is those used to train the data, and then you have a left out validation set, which is used to evaluate it. And you can see the bigger and bigger you make the training set, the more like it is, the more its performance is going to be similar to using all the data, right? Because it's not that different. So there's a real advantage to doing it in that way. But that means that the validation set's small, so the estimate of the risk is going to get more and more noisy. So there's this balance back and forth between how to do this. I mean, generally, if you have very, very small sample sizes, you want to use high folds because you have already very little data. And if I'm breaking it in two, then the performance I get back estimate's going to be very different probably than the full data set. And therefore, you want higher folds probably. If you have very, very large sample sizes, then you may not have to have that many folds. You could just have, V could be 2 or 3 or something like that. So generally, higher folds are better for smaller sample sizes. And yep.
Do you guys do repeated cross-validation?
Well, the theory is developed for non-repeated, which means it'll definitely work for repeated, because that's an additional smoothing, right? There's some element. It's an interesting point that for any one sample, any one way you split, how I ultimately end up with my final model will be somewhat tied to how I split, right? If there's random components involved in the data adaptive part, and if I split differently, they're going to add some variability, and that's noise, right? You really like to get rid of that variability, so you can actually redo this whole procedure again and again and again, and then sort of average the predictions that you get back from each of those procedures. And it's possible you can gain, those gains are second order, meaning for a large sample size, they don't help you at all, but for smaller sample sizes, it might help some. That's not typically implemented in our stuff, but it's still an interesting addition to make. My guess is the benefit goes away pretty quickly. The sample size gets large. And the idea is that we're going to change the role of different samples in different iterations of this. So in the first case, it's taking the first, the 9. These are arbitrary chunks, right? Just 9 arbitrary chunks that you made. Going to fit the various models that you're interested in trying on the data and evaluate their fit, evaluating the average loss or the empirical risk on this left out one. And then you'll throw that one back in and take another one out. Maybe you'll take 9 out and 10, and all these will be the training set, and you'll redo it. Always the validation set is independent. Yeah?
Sorry, just want to make sure I understand correctly. So when we have repeated measures from the same individual, say we have 100 individuals, each individual generates like 10 observations.
Okay.
And the way we do cross-validation is we split by individual, not
Yep.
by observation.
Exactly.
Okay, so we run.
You would split up 10 individuals, and all observations from every individual would be in the same validation set.
I see.
Yeah. Therefore, you still have the independence, right? That's what the key is for the theory to work. So, I went over this. They're in the training are used to construct the candidate estimators, those different algorithms you can try, including standard regression, et cetera. And for each of those fits, we evaluate how well it does on the validation set and store it, right? So that validation set, we get the risk for, let's say I have 5 algorithms I'm going to try. Just going to use the mean of the outcome on the training is one estimate. That's going to use to predict on the validation, so everybody will get the same prediction. which just be the mean and the training. I could use just standard logistic regression. I could use stepwise logistic, cart, et cetera. I'll fit all those on the training. Each of those provides a prediction on the validation sample. So if I have 5 algorithms, I get 5 predictions. And then for each of those things, I also have the observed data, the observed outcome, and I can estimate the loss for each observation and the validation for each candidate. So I get 5 columns of loss functions then, and then I can average each of those columns and that validation to get an estimate of the risk in each one of those. And I can, of course, if I just did this once, I could just compare those, but that's just using one small slice. And of course, I want to get some of the variability that you were alluding to. Ted, right? Chris, damn it, Chris Kinney. I know there's Ted Kinney. Okay. Ted Kinney is a different Kinney. Chris. And so you don't want to just evaluate it there. That would still work in some sense, but it's going to be variable, right? So you want to take this one back in and try it again and get rid of some of the variability that you see across the fits on each training sample, and particularly the estimate of their fit on the validation sample. So we're going to average those risks over each configuration we have, where we leave one out and use the others to train. Right, so in the end, you're going to get, for every candidate, you'll get 10 estimates of the risk. And then you average across all those, and that's the average risk for each candidate, and then you can choose the best one. That's one method.
Could you clarify why using more folds is better for smaller data? I would think that's
Oh.
a little counterintuitive, because if you use more folds, wouldn't you run the risk of not having enough observations in each of your training sets?
Yeah, I mean, it's only, the way I think of it is this way. And you're right, that's a good point, because you also estimate the risk more poorly, because that's getting really small, right? Is that when you estimate on the training sample, you want its performance to be similar to what you're gonna get in the full data, right? You don't want it to be drastically different. Because if it's drastically different, that message, what you're gonna get back is gonna be something very different than if I had selected based on the full data. If I had a sample size that was as big as the full data in a separate test set, I'm gonna get something very different if I use half of that to fit it, because the fits are so dependent on sample size. When sample size is small, they really change drastically, sample size grows typically, that you can get fits that are just drastically different, and something that's just underperforming. Because in the end, you really want something that works well, right? You also want a good estimate of the risk, which helps you choose between the things that do well. So it's not, there is no free lunch here. You are exactly right that you can't say that, oh, I won't screw up if I do that because I'll estimate the risk so poorly. I'll choose among those in a way that's just based on noise and not the actual performance. The hope is when I average the risk across the 10 folds, I get rid of some of that variability, and there's some evidence that's true, so there's a little less of a problem there than in estimating the risk than there is in the fact that the actual fits won't be anything close to what could be done if I do something close to the sample size. And that's my justification. It's ad hoc, but I have to say in practice it generally works pretty well. I mean, if you're fitting very adaptive things, the difference from a sample size of 50 to 100 is huge. The difference between 10,000 and 20,000, not going to be as huge probably. So that's the main reason. Yeah.
Is there any benefit to running default cross-validation several times when you?
Yeah, that's what Chris was saying.
Okay.
Yeah, there could be it's a second order problem. That means for large sample sizes, it won't be a benefit, but for small sample sizes, it could be. We're not talking something that's implemented in that way, so I'm not gonna go over it, but it was a good point, because in any one split adds randomness, right? That randomness kind of goes away as sample size gets large, because the data generating distributions now are gonna be pretty identical, the empirical distributions, as sample size is large, and therefore you don't have that variability. But yeah, that's a good point. This just shows it graphically. If it's 10-fold, I remove the tenths the first time, and then estimate it with the 9, get the predictions in the 10th, throw the 10th back into the training, but now take out the 9th, redo it, etc. Right, till I get to the last one where I remove the first one, and fit on the remaining 9. So this is how it's implemented. It just loops through the validation samples. Yeah.
Also kind of on the small data front, would we want to consider potentially blocking unimportant covariates when we do the cross-validation samples?
Oh, you mean sort of matching, make sure the distributions are the same.
Yeah.
Yeah, if you, those kind of things, they don't bias the estimate of the risk because you're keeping it, you're still using the empirical to do it because you're just matching the empirical essentially. And yeah, they could reduce some of the noise, so it's possible that might be a good idea. I mean, again, it'll be a second order phenomenon. Yeah. So, a lot of things, there's a general, here's the general rule between, for those interested in just a vague idea of how the theory works in statistics, at least in this context, that, we develop procedures based on the asymptotics, because you can rarely prove things in universality for finite samples where these so-called second order phenomenon are still important because they're unpredictable in finite samples. They're predictably small in large samples, which is why we can say in small samples I can ignore them. And what's left is much more predictable, the behavior of these things. So for finite samples, you can use a lot more, you have to use more ad hoc kind of approaches to account for this non-robustness that you can get that doesn't match the asymptotic predictions. And so in the finite sample case, there are a lot of things you can do that sort of won't matter or are not even theoretically justified necessarily asymptotically. You just want to make sure anything you do for finite samples to make it more robust won't have any impact in the asymptotics. And that's the way these procedures are developed. There's all kinds of contexts where these kind of small sample adjustments to the algorithms are used to make sure you try to reduce the impact of these second order phenomena that are not second order because they still have a big impact in finite samples, but in the limit they have no impact. And this would be an example. I could bootstrap the cross-validation, essentially just redo the cross-validation a bunch of different times. That would be a small sample, finite sample kind of approach, because I know it won't have an impact in a large sample. The asymptotics would say you don't do it because it doesn't have any impact, but it can in finite samples because those second order phenomena, the fact that each validation sample won't have essentially the same empirical distribution anymore goes away because of just the randomness. If I'm only selecting 10 at a time, I can get unlucky. I have 10 people that are all the same gender or whatever it is, right? And that's, we justify things typically with asymptotics, we become an estimator, and then we go back and say, okay, when we simulate, does it start screwing up for small sample size and not showing the behavior that the theory predicts and we find out it might be true? You can look either technically the second order terms or use intuition to create other procedures that say, okay, if it looks like it's screwing up by some summary statistics, do something else, like do this cross-validation more than once and things like that. But anyway, I don't mean it so much for this lecture, but in general, those are the kinds of ways we justify estimators and why sometimes there's finite sample concerns that take the original estimator, modify it so it works more robustly for more sample sizes. And in the end, we are trying to make machines, so we want the machines to work regardless of the sample size you put in automatically. And so these procedures become important. That being said, I'll ignore that for the remainder of the course. And then, I already explained this. You get a risk estimate for each candidate in each validation sample. You average them across all validation samples, and you get the average mean squared error, for instance. This is the important point. This is why this kind of approach becomes very powerful because the kind of estimators that we're using don't require us to have parametric models. We just need something that predicts. Doesn't matter, it can be a black box. We don't have to even know what it looks like. We don't have to limit ourselves to the kind of traditional techniques you're used to in this approach. We can add all kinds of different things. Some things can be highly adaptive, and some things can be just prefixed as simple regressions, as I mentioned. there are lots of fancy approaches out there. So again, because there is no universal best way to do it, means anybody with a clever idea can publish an algorithm, right? When there's theory, you're kind of constrained. It's kind of annoying because if I propose something, I have to justify that it's better than something else proposed. But machine learning, you don't necessarily have to do that. So it just proliferates algorithms. There's so many out there, and it's good because it turns out the theory tells you want to try a bunch of stuff. And because the academic environment in machine learning generates a bunch of stuff, we can use it. But it's pretty unconstrained, and there is a ton of things, you probably heard of, and some you probably haven't heard of. And when we actually implement this practice, there's an existing library of these things. You don't have to pick them out of the blue. There's a bunch of candidates that have already been implemented that you can easily get, particularly if you're using R. The thing that's also interesting is many of them are data adaptive themselves. So a lot of these algorithms when you're fitting on the training sample, they'll do cross-validation within the training. So you'll have nested cross-validation, which is why these techniques can sometimes take forever because you have nested loops going on and there's a lot of work going on in each one of them, which is also why we're trying to implement these in more scalable ways so we can use many different computers simultaneously, many different processors simultaneously to do this because there's so many parallel things going on. We should use that, not do one and then the other and the other. We should just do them all at the same time. And that's some implementations of these algorithms do that to make them relatively fast. But the standard ones can be quite slow if you have a big data set and you're using lots of algorithms. We'll refer to whatever set of things that we're trying as our library. That's just syntax. It's just a definition. We're defining our library of regression models and procedures are set as a library. This is sort of the Bible of all the kind of algorithms you could use. It's a reasonable book, and again, it's written in this way that is rather ad hoc because there isn't a lot of theoretical justification for any of them. But it's a good kind of library itself, or a good encyclopedia, I should say, of machine learning algorithms. And there's, I've talked about this, all kinds of forward stepwise regressions you can do. This is a version of stepwise where you can each stage, you can either delete a variable or basis function, you can substitute an existing one with another one, or you can add one. So it just adds more steps to each step, essentially. It's a more flexible algorithm than just standard stepwise. There are these things that are based on smooths. So for continuous outcomes, continuous predictors, even if there's more than one, it can fit smooths for all of them. They're called additive smooths, and it might look like, Q-bar, something like, plus, I'll say S1, W1 plus S2, W2 plus, and these are all, these are parametric functions, just the beta 0, beta 1 times A, and then these things, right, these S's are unspecified smooth, so they're semi-parametric. They can't be any shape, they have to be kind of smooth, but they don't have to be smooth in any particular kind of way. They can, they just have to, at some level, they can't be too rough. Like that's too rough, but the other thing is fine. And the level of smoothness can be defined to make them very, very smooth or a little bit rougher, right? So Mars is one way. It's doing it with kind of parametric splines. They're called linear splines or quadratic splines, and that means they can break up let's say I have this is they break it up and they bend it at places called knots. This might be W1. Oh, I should just put W, not, that's a knot, and then another knot, and you get piecewise linear splines, and they tries to find the knots to bend it the best possible way. It has its own built-in way of doing things trying to do the best job it can, right? It's gonna be a black box to you. It has its own internal thing that it's going on that you just let it do. And the good thing is you can evaluate it because you've left the validation sample out. That's why this kind of, it's a very simple procedure, and it doesn't means you don't really have to understand necessarily what's going on behind the scenes for all these candidates, because you have the data to evaluate it in a very direct way, where you compare the observed to the predicted and see how well it does on average, right? So it allows you to use things where you don't really even have to understand them, and if it turns out it's terrible, it won't select it, right? So there's not much risk to putting things in that are horrible, because they won't do well on predicting in the validation sample, right? Because you can't overfit, because I didn't use the data to fit them that was in the validation sample. Random forest is a very popular algorithm. It's implemented in a pretty efficient way. It works well in R because they put a lot of time programming it. It's a bunch of trees. You make one tree, regression tree, which you might have seen, which is really, you can think of as histogram regression. It's just a way of breaking up the covariate space into chunks. And you say, okay, for this chunk you get one prediction, for this chunk you get another. It just makes a whole bunch of trees. Trees are terrible predictors usually. They're used often for explanation purposes, which is not good. They shouldn't be, because there's nothing to say that you data adaptively choose a tree. It's going to give you the true underlying model and the variables that are most important. There's a lot of randomness that can come from making a tree, which you can find just by bootstrapping and refitting another tree. They won't look the same oftentimes, depending on the sample size. So random forest fits a bunch of trees and averages them. And by doing that, it smooths across the variability in the trees. And it turns out, by almost sheer luck, the thing works great. There wasn't a lot of theory to justify it, but it works really well. And it's based on this principle called bagging. Bagging and bootstrap aggregation is a very similar kind of thing. You're just basically averaging across a bunch of different fits, okay, within that algorithm. Again, it's just a black box that you're fitting on the training. Neural networks and other things as well. There's, this is a tiny list of what you could do. There's a whole bunch of these things. There's 41 packages for machine learning right now in R, and I'm sure that's probably outdated, because I know it's outdated because I have a student that posted another one. And so again, and there wasn't a great theory for it. It was just something that was kind of missing. It had to do with something called lasso, and it just, so I just wanted a different kind of predictor that the other ones weren't covering, and so that's added there now. So there's a whole bunch of these things. Okay, it's basically the bottom line. The most important thing is there's a lot, and there's no universally best one. That's the two effects that you need to know. Yeah.
So when you're pre-specifying these types of methods, how do you do that?
How do you choose the set of algorithms?
Yeah, how do you just like decide a set of algorithms that you're going to use, and then that's how you write what you bring out?
I mean, there's some guidance in how to do that. I have my own. There's practical concerns sometimes, like I need to finish this before tomorrow, and this algorithm will take a week. So, right? So there's some things that have to do with computation. Some of these algorithms are really well written, so they're robust and they don't fail. Some of them are super fragile, like, if any kind of, they make errors that you can never figure out what the hell the error is. They just give you something and it's just completely opaque what actually goes wrong. There are some rules, or some principles. You want to choose algorithms that are both very adaptive. And when we're really talking about estimating causal effects, I'm going to have a big caveat on that. But for now, for prediction, that are very adaptive, and you also want algorithms that are very smooth and aren't very adaptive, because you want to make sure you're covering both areas of the variance bias trade-off. You want things that are going to be lower variance and higher bias, and things that are lower bias and higher variance. And so, again, as I answered Courtney, the main thing is you almost can't put too many algorithms in, is what the theory tells you. So as long as your sample size isn't ridiculously small, if you find an algorithm, put it in. That's basically the bottom line. But you don't want to just put linear regression in and stepwise linear regression. That doesn't cover very much possibility, so that would be a mistake, right? And you don't want to do something that's necessarily just highly adaptive, because it could be that your data is pretty smooth, that the regression function is like a polynomial or a line. In that case, you're wasting a lot of parameters. It's going to be highly variable when it would have found an easier way to fit.
And should you also take into account things like the number of variables you have?
Sure. So that's a really important one. I'll take a little, let me just take a little pause. As so-called tuning parameters. So each of the algorithms, you can also fit different versions of them. Because like, for instance, if I'm doing stepwise, I can say, only enter a predictor if it has a p-value less than 0.05, given everything else in. But I could also change that to 0.1. That's a tuning parameter. That will give me a different model. That's two different candidates now, right? And I could do that for a sequence of p-values if I thought that was a good way to do it. If I'm fitting things at using smooths, I could try different levels of smoothness, right? So you can, even from a single algorithm, you can generate many algorithms that you can try. Is that you? I didn't mean that. Is the door? Yeah. Okay. Anyway, there's a lot to learn about machine learning, and again, it's very ad hoc to learn. It's kind of hard to learn in some unified way because they do lose different procedures, and there isn't a universal justification. Just know that they're out there, and that's all really we need to. Yeah.
Quick question.
No problem, yeah.
Screening algorithms in SuperLearner?
Yeah.
Does that allow a different set of variables to be used for each given algorithm?
Mm-hmm.
Okay, so if you're after a set of variables,
You can also screen
Okay.
differently. I can
Okay.
use just bivariate correlations to screens. They only take those ones that are significant and just that X versus that Y, or I can use other screening, there's lots of screening algorithms. So
Okay.
I can pair those. I mean, the combinations are infinite.
yeah, but
So-
there's no way of telling after you run SuperLearner which variables were actually ended up being used.
No, you can.
You can?
You can figure it out in the end.
Okay.
Yeah,
Okay.
definitely. I mean, I'm not saying that's a great measure how important they were. It obviously means something, but that could be highly variable. So in other words, that may not be a robust measure of importance. So, I already went over this. It's hard to choose what to choose. A priori was going to be the best. That's why proof's in the pudding. You want the data to decide, and the best way to have the data decide is to use cross-validation. Here's just an example of cross-validated risk relative to main terms regression. So other procedures and different studies that have different, they're just different studies, right? One thing about this is like I don't have to simulate to see how well it does. I can use the data itself to see how well it does. I can use that cross-validation to get an estimate of how well it does for the data. So what's nice about these things is you don't have to like simulate necessarily from highly simplified situations. You can just use the data that you get and try the different algorithm and get their cross-validated risk. And here's an example of the relative mean cross-validated risk, as we talked about getting for these different kinds of algorithms, least squares versus these ones. And if you look at here, well, here's the best one. That's the smallest, right, relative to it's just relative to this. So it's, it's a fraction. It's really doing quite well compared to least squares. But in this study, it's a different algorithm, works well. Probably in this case that the truth was something that could be modeled well by splines, obviously, since it did so well. In this case, none of them did all that great compared to least squares, just a little bit better. These are all bigger models than this. So they all can include both the main terms and other things, or submodels. And then this one, a different one, Mars did well, and this one, DSA, which we haven't talked about, but it's deletion, substitution, addition algorithm. It's like stepwise, did the best. So you can just see from these are real studies, 4 of them. There is no best there's no best universal one. For some data sets, different things will be favored versus other data sets. I'm going to stop. I'm just tired. I know. I can look at you and see you're tired. So I'll just stop and answer questions here, and then we'll start. We have time to catch up. we're fine, so I'll start this up next time. Any questions? Yeah,
You think in a decade we'll all be obsolete and we'll just be able to
Yes.
data set like Google?
I mean, the goal that we're working on is to have algorithms where we don't have a job. That's the goal. And I do think it's possible, actually, that it's possible now if we had enough programmers working on it to build algorithms that would require almost very little user input now, and not so much background knowledge. And the goal is you want people to concentrate on the science and the substantive parts. I mean, statistics has always been treated like a nuisance in some way, in collaborations, and it's relied on the sort of priesthood. Like you can think of statisticians, they come in, no one knows what they're doing, and you just have to sort of defer to them, and that's never comfortable. You really like an algorithm that's written based on first principles, that's optimal in a huge number of circumstances, and that's possible now. It's just not implemented yet. But in 10 years, yeah, maybe.
Isn't one challenge of SuperLearner that it's only optimal among the algorithms that you try?
Yeah.
And you never know if that one, like you didn't put SVM in, then it would have done better than what SuperLearner found.
Right, and we haven't got to it yet, but we'll get to it. Also, the theory tells you to try a bunch, so you shouldn't leave out something.
But also, it's only optimal among the hyperparameters that you test. There's
Yep.
an infinite space of those.
Yep.
So you never know if a different hyperparameter.
Yeah.
would-
You're asking very practical questions, like how many, you can always, it's only going to be optimal in choosing the best one of the candidates, or best combination of the candidates, right? You can't come up with a theory that says any of these are ever optimal universally. So that's always going to be the gold standard among what you put in there. If you put in everything, or something that covers the entire space that you're pretty comfortable with, then there won't be anything better because you had everything in there. But if you don't put in everything in, then yeah, sure. Definitely. Okay, thanks.